Well, thank you very much, guys, for coming. This is some work that I have been doing as part of the Frontier Development Laboratory, which is a summer program that puts together domain scientists and computer scientists to tackle problems of relevance for NASA. And so I will talk a little bit more about that. So there has been 2 years. This is the second year for which we have a heliophysics team or heliophysics teams. And I was a mentor this year and a mentor last year. So these people that you see here are 4 participants, which were the main heavy lifters, although this is in alphabetical order. I will show you later all of them. And the other mentors. So all these people that are here were mentors and team members. And so I'm going to start with my take-home message. What I want you to take out, the most important thing that I think is I want you to take out of this presentation. The first thing is that measuring solar irradiance is important for us as a technological society, and that's why we do it. The second thing is that we lost our capability to measure part of the EUV spectrum because one of the modules of EVE failed in 2014. But we can use neural networks to plug this EUV observational gap. So that's basically the main result that we have. And also, I will give you a little bit intro about how these algorithms work and what I think they're good for. And especially, I would like to do a lot of advocacy for them, I guess. And the fact that these are not necessarily black boxes. And so I will tell you a little bit of what things we may get out of them too. So to begin with, the first part, which is to measure the solar irradiance, is important for us as a technological society. And so I want to start with one of my favorite images ever, which is the solar spectrum. And I believe it's measured. Does anyone hear if this is measured on the ground? Yeah, I think it's measured on the ground. So you have here also the absorption lines of our atmosphere. So it's a really beautiful thing. Okay, so for those that you may not know, although I will expect most of you probably do, irradiance is the amount of power per unit area that we receive from the sun in the form of light. And when you do this for a specific wavelengths, it becomes spectral irradiance. Okay? Why do we care? Because irradiance basically is what keeps us cozy and warm. Right? So it's a big input to our atmosphere, and any variations on irradiance can trigger changes here on Earth in terms of climate. And that is, for example, all the glaciation is changes of irradiance introduced by changes in our orbit that can trigger all these things. But we also care as a technological society. And so what you see in this movie is a really nice movie, is all satellites that have been launched since the first one, in yellow, operating satellites, that gradually become junk or pieces, right, with the pass of time. And so there are about 50,000 tracked objects in this moment. And you can see that the great majority of these objects is close to Earth. Now, this means that these objects are in a place where they can interact with the upper part of our atmosphere. And that part of our atmosphere is strongly affected, in particular, by EUV irradiance, ultraviolet irradiance. So here is the spectrum of the sun, as you see it at the top of the atmosphere, without any atmospheric absorption. And here is the same spectrum at sea level. And so you can see that a big part of this energy is being absorbed by the atmosphere. And in particular, we're interested in this part, which is the EUV. Now, different parts of this spectrum get absorbed at different heights. And so this is a nice adaptation of an image that I found. This was done from the point of view of what you can use to see out, right? And so you can use telescopes to see out in the radio and in the visible, but there are other wavelengths that don't make it to the surface. Now, if you look at ultraviolet, this part of the spectrum here, it gets absorbed very high in the atmosphere. So here is the same idea, but a little bit more detailed. Again, so here you have wavelength in the x-axis, and in the y-axis you have altitude. Now you can see there a color, like a space that is filled with color. Different grid squares in this image are telling you how much energy is being deposited for a given wavelength at a given height, a given altitude. And so you can see here the ultraviolet, which is in this part of the spectrum, is being absorbed at a high altitude, 150 kilometers, between 100 and 150 kilometers. And it's a lot of energy, more than in other parts of the spectrum, okay? Now, what drives EUV variability? Changes in the solar magnetic field. So most of you probably have seen this. It's an HMI magnetogram. The magnetic field here color is giving you polarity. Red and yellow is magnetic field that is going into the screen. Blue and green is magnetic field that is out of the screen, right? You can see the active regions, so the bipolar structures that give structure to the solar magnetic field. And if you look at this in an EUV wavelength, which in this case we're looking at an AIA image 171, you can see that this magnetic field is basically giving structure to the corona. And so as with the magnetic field, EUV irradiance changes in what you will think about as 3 different time scales. And so here I have just this movie for a full rotation, right? You can see that there is a lot of stuff going on, flares and changes of the structures in the corona. This will give you the short-term variability of the EUV. But you can also see that the sun is showing us different phases. So the rotation of the sun is also a source of variability, just because we're looking at different structure that when it comes around retains some similarity of how it looked when it looked at us first. And then, of course, you have the variability that is driven by the solar cycle. So here is again, I believe is 171, but measured by SOHO, EIT. And so you have 1 image per year during 11 years during solar cycle 23. And so you can see how it is much darker when there are no active regions and you're at solar minimum. It gets much brighter as the solar cycle progresses, and then it becomes dark again. So the motivation behind this project was that we lost our capability to measure part of the EUV spectrum. And so all the data that we use and what we were using to measure that part of the spectrum was thanks to the instruments in the Solar Dynamics Observatory. So SDO, you probably are familiar with this too, has the HMI, the helioseismic magnetic imager. It gives you Dopplerograms. It gives you, when you invert the data, you get magnetograms, and it gives you the pseudo-continuum, which is here in this part of this mosaic. This is an imager. And you also have the atmospheric imaging assembly, AIA, which has EUV narrow band imagers, 9 channels, which you can see here, and they are mapping plasma that is at different temperatures and it's at different heights, okay? And then you have the EUV variability experiment, EVE, which is a EUV spectrograph, so it gives you spectral irradiance, so the amount of power that we get per centimeter square, but spectral with high resolution. And you can see, but it's integrated, sun as a star kind of instrument. And here you have in this plot a measurement of the EUV spectrum. And the x-axis you have wavelength, in the y-axis you have irradiance. And here you have the different modules, EVE modules, that are mapping different parts of this spectrum. In 2014, this instrument makes a diet. And so you can see here that we basically lost access to one of the biggest, most energetic parts of the spectrum from the point of view of the radiance that we get and absorb here on Earth. And so just for comparison, here is again the image that I had shown you, where you have the wavelength and you have the altitude. And basically, we're no longer, we have gaps in this region here. Oh, by the way, I forgot to mention this. This line here, it is the, what is it? This is dense temperature of the atmosphere at different heights. And one line is a solar minimum, and the other line is at solar maximum. So you can see the impact that EUV variability has on that part of the atmosphere is big. And this makes it so that you have, it's important, strategically important to make orbit prediction. And for example, I was reading that the International Space Station needs to boost its height periodically. And depending whether you're here or you're here, that boost has to happen every a few weeks or a month or so. And so you have to plan it. That's one of the reasons why people want to plan this. So the NASA FDL, the Frontier Development Laboratory, is a summer program that brings together these researchers from domains and computer science and put them together to solve a problem of NASA relevance. And there are a bunch of, both years they have been, it has been running for 3 years now. Heliophysics has teams in the last 2. But you can see here all of the things that they're looking at. And now there is one here in the US and another one in Europe. So this year for space weather, there were 2 projects, one of which was seeing if we can reconstruct the missing MEX-A spectrum using deep learning by ingesting AIA images. The second one was trying to forecast the impact of solar wind variability on ionospheric conditions. So that was the other project. I was part of the Irradiance project. These are the team. So we had 3 computer scientists, Richard, Alexandra, and Rajat, and 1 domain scientist in the team. So these were people that were there for 8 weeks, day in and day out, working on this project. We had 3 heliophysics mentors, which were there at different moments in time, sometimes overlapping and sometimes not overlapping, which is Mark Chung in Lockheed Martin, Meng Jing, who is now part of SETI, and me. And we had a data science mentor, David Fuhi, who at the time was a postdoc at UC Berkeley, but now is a professor at the University of Michigan. So typically when you want to reconstruct the EUV spectrum using AIA images, you do what is called a physics-based forward model with an inversion of temperatures. So the amount of light that you receive in an AIA image is some form of it's an integrated measurement along the line of sight. So the solar atmosphere is optically thin, and you're looking at plasma all along the line of sight. So you're integrating along the line of sight, and in that line of sight, you have plasma that has different temperatures and different densities. So typically then what we do is we use AIA images to try to make an estimation of that density and temperatures along that path. And once you have that, you can use a physics-based model knowing the properties of that plasma to reconstruct the full spectrum. And this part, the first part, is called trying to make an assessment of the differential emission measure, which is essentially that combination of density and temperature along the line of sight. And here you have the response in temperature of the different AIA channels. So 94, 131, 171, and so on and so forth. And you can see that these channels are responding to plasma of a different sets of energy. And a little bit in the sense as our eyes do, where we have receptors for different, that have a wavelength pass. And so we combine those, even with overlaps, to get an assessment use of color. You can do something like this by taking advantage that different channels have a very different response to temperature, even though they have overlap. But this is a very difficult problem, and it is undetermined. You don't have enough information on your AI images to make a full reconstruction. So what we do is an iterative process that minimizes some form of error function, but sometimes it doesn't converge, and we don't know exactly if the convergence is unique. But it works well. So it's just super expensive, and it's hard to do. And then once we have this, then as I told you, we can reconstruct the entire spectrum using the properties that we know, astrophysics databases of the emission of light from plasmas. Okay? Now, we did an implementation like this, which we don't claim is the best one in the market, but we wanted to do something like this as a baseline. And so what you have here is one of the MEX-A channels, the helium-2, which is particularly difficult to reconstruct using the other approach that I just told you. And so here in the left, you have a 2D histogram of the observed versus predicted irradiance on helium-2 channel, right? With the Y, this is in logarithmic scale, both X and Y, with the Y equal X here as a black line. And the idea, of course, ideally, is that we are going to fall perfectly there. Here is the time series for 2012 and 2013 for both predicted and observed. And here is the relative error. And so what you can see is that for this channel, the relative error is somewhere around 10 to 20%. If you include all MEX-A emission lines and combine them together to get a single unit of measurement of error, it's about 5%. The idea then is, what if we basically skip this whole path, the path on the top, and we use deep learning techniques to connect directly our input images with our output EUV spectrum? Was basically the idea. And the answer, of course, is yes. I will show you. So what is deep learning? So the people in the industry basically think it's like a magic hat that can do anything, pretty much, right? And the advocates think it's a silver bullet that can be applied to any problem. The skeptics don't like it, see it as a black box. And the general public basically thinks that it's going to be the end of our species, okay? But in reality, it's just a tool, right? And although we don't know if this is indeed going to be the end of us, it is really a tool. And one of the things that I wanted to highlight, although it's a challenging thing, is that it is not a black box. You can mine it. And as with this Swiss knife, it can give you insight. And one of the challenges of using these techniques as a scientist is getting that insight out, especially because people in the industry don't really care if you understand or not. It's very effective. These are very effective techniques for certain problems, and they outperform humans now in many fields. But for most applications, people don't really care why it works and why it doesn't work. Whereas for us, it would be very interesting to be able to use it to gain insight. So, what is deep learning? From Wikipedia, it's a class of machine learning algorithms that, one, use a cascade of multiple layers of nonlinear processing for feature, structure, and transformation. So this is where part of the idea we can get insight here is that as you go through the different layers of your structure of your machine learning technique, you're making abstractions out of the original data. And the second thing is that it can learn multiple layers of representations that correspond to different levels of abstraction and form a hierarchy of concepts. Now, in particular, the ones that we use here, and this is a big family of techniques, but the ones that we use were neural networks. And so neural networks is basically a way of connecting the input data here with an output, right? You want a neural network, and the idea is that this neural network is on its own going to figure out what are the most important pieces of information that connect something with something, right? And you're not going to, the only inputs that you have on that is the samples. You tell it, this is connected with this is connected with this is connected with this, and gradually the thing starts learning to make this connection. Now what you're looking at here is called the multi-layer perceptron and was the original neural network. So you have your input, and let's say this is our input. Your input is input to every single neuron in the next layer, and the output of those neurons is connected to every neuron on the next one, and so on and so forth, until eventually you get to your output. Now, when you have data that has a lot of parts to it, each one of these connections is a free parameter that can be tuned. So when you have images that have a lot of parts to it, you can very quickly end up in a regime with millions and millions of free parameters. And so now the other thing that is important is that neurons are basically, each neuron basically does is it takes all the inputs and makes a linear combination of them and spits it out. It's just a linear combination. But on the other side, before it goes to the next layer, you cross it through a nonlinear function. And so the nice thing about this is that it gives the network the ability of giving weight to different inputs, saying this is more important than this. And also through that nonlinear function on the other side, you can capture nonlinearity, relations that are nonlinear. Now, why is it cool, deep learning? And I don't see deep learning as in competition with any other traditional method of interfacing with data. But I see it as another technique that basically empowers us as researchers. And so I'm going to show you something that is fascinating, a quick experiment. Some of you may have seen it before, in which case, please just keep it to yourself. It is a test, and I want to see how well you guys perform at this task. So it is a video, and it goes like this.
This is a test of selective attention. Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla?
What? Yes.
Did anyone not see the gorilla? Okay, some people see the gorilla, some people don't see the gorilla. I saw the gorilla because I have a very hard time dealing with a problem like counting those passes. So after 3 passes, I just don't know how many, and stop looking at that, and then I saw the gorilla. But if you are good at counting those passes, odds are you will not see the gorilla. And what is the thing here? The thing is that we are creatures of finite attention span. We have a finite bandwidth. When you give us an input or a bunch of inputs, we're all the time masking in sensorial input. In this moment, there is a huge amount of sensorial input that we're receiving, and you are focusing on my voice, for example. A lot of all the noises that are here, there is a little drone that you can hear, and there is someone drinking, and so there is a lot of stuff going on, but you're probably just in this moment filtering all that and focusing on my voice. Now, the nice thing is that deep learning, these kind of neural networks are creatures of infinite attention span. So if you show it a huge amount of sensorial input, they can and will pay attention to every piece of it. And so that is the powerful thing about combining the human researcher with the deep learning algorithm. Of course, they have limitations too. So here is an image. This is actual a real screenshot that I took. I Googled hands in Google Images, and these are the images that I get. Now, do you see any issues with these images that the Google is showing me? Well, one of the issues that cause like discussion that I want to point out is the color of the skin of the hands that is showing you. Right? There are very few non-white hands. And basically the idea is that the people that trained these networks just picked, it may be when you go to like one of those databases online, like where you can buy images and so on and so forth. The majority of the images that you have of hands are of white people. But then this is one of the things that is you have to be extremely careful of how you pick the data that you're going to use to train your network. Because if there is any bias in how you picked it, that bias is going to sneak its way into your deep learning algorithm. Because the deep learning algorithm is completely naive. I don't know if you ever saw this news. This is again the same kind of idea. So Microsoft made an AI that was supposed to be able to, you could chat with it, and from the things that people will tell it, it will learn. And so the idea was that it was going to enrich the repertoire of phrases and interactions and learn them, and then become a more and more sophisticated person to chat with. But a bunch of trolls started just putting completely inappropriate things, regardless of what how the chatbot was reacting. So Heil Hitler, kinds of things like that, again and again and again and again and again and again. And then within a day, this is basically all this thing was talking about. So it's again, whatever you show to this has a huge impact on the kind of abstractions that it makes. No criterion. And then, of course, this is one of my favorite images ever, is the fact that sometimes things look very similar to each other, even to us, right? And so it is possible that these algorithms may not be sophisticated enough to make the distinction. So anyway, this is one of my favorite things. I'm going to let Lisa take a picture. So deep learning algorithms are naive and single-minded in the way they learn, right? And that's where I think the biggest weakness is. That's why it is so important to pair them up with the human. You are the person that provides context and criterion. And training data and selection is absolutely critical for their success. So this is the other thing that is, so basically the biggest challenge when you do this kind of work, is always selecting your data. You take and how you break it, how you partition it, and these kinds of things. That's where you spend the great majority of your time. And that's what most people that do this for the first time, including myself, make the greatest amount of mistakes. So when it comes to image data, we are basically on the crest of a revolution. The idea is that you have an image, right, which to the computer just looks like a bunch of numbers, right? And in this case, like the first and most visible applications of this kind of techniques was image recognition. So I will show this image to the computer and it will tell me that it is a cat or a dog or a hat or a mug, for example. But you can do classification and you can do regression. In this case, you have images of the sun as an input and you want to get some value of irradiance. So both are possible. The cool thing is that the revolution came when people came up with what is called the convolutional neural network. So if you take the most powerful form of a neural network is a fully connected neural network like the one that I show you. That's the most versatile of all. But it very quickly becomes impossible to use if you have an image. Because now your input can be, for most of these applications, they do 256 by 256 images. But if you have something, and those 256 by 256 images are 3 channels, red, green, and blue. And each one of those pixels can have a value between 0 and 255. Now, if you think about something like a solar application where you have 4K by 4K, and the dynamic range of one of these images is 5 orders of magnitude, and you have 9 channels of that, very quickly becomes a very, very hard application to do. So what people realize, and they inspire themselves on the way we see as humans, the way we process visual information and are able to say, here is Lisa, and here's the screen, and I'm going to grab this, is at my glass, right? Is that your first layer of neurons, your layers of neurons now share weights and have a visual, like a field of view. So you have a layer of neurons that is arranged like this. Each one of them has a small field of view. All of them are sharing exactly the same weights. So out of the image that is 1K by 1K, you're taking a small image that is 30 by 30, and that gives you 900 weights. And those 900 weights are shared by this neuron and the one beside it and the one beside it and the one beside it and the one beside it. So now you significantly simplified this. And now what you do is you have like different paths of information where you have a layer, like one layer of those neurons with shared weights looking at the screen and another one looking at the same image. And so you have several of them. And the way they interact with your screen is a little bit like, it's a convolution. So it's called convolutional neural network. Now the cool thing is that these things, if you train a neural network, a convolutional neural network, and then go back and look at the weights, these weights now look like little patches. So they look like a 30 by 30 image. And so you can see what kind of this looks like. And when you realize, and this is just a conceptual thing, but it is more or less like that. Your first layer, so here's your image, and it inputs to the first layer. And these are the kind of filters that you get. So basically, the neural network starts, when it starts interacting with image, it starts interacting at the most basic level, edges. Right? So you can see here, for example, that this is an edge like in this diagonal, and this one here is an edge in the other direction, and blobs, so it's looking for a blob here, or a blob here, and blob here, and so on and so forth. So that's what a convolutional neural network typically does first when it interacts with an image. But then you take the output of this, when you convolve an image with one of these, you basically get something that looks like your input image, but now it only highlights vertical edges, for example. And we call that a feature activation map. And you feed that into another layer of convolutions. And so what is start happening is that as you go through different layers, the next layer is using information from this layer. Where are my vertical and horizontal edges to start identifying more complex structures? And so conceptually, in this example, is you start with edges and blobs, and you turn them into noses and eyes, and then you turn those into faces. So this is the abstraction, the ability of abstraction and combining into a more complex concepts along the path in which your information travels. And that is very much like how our brain works when it processes what you see. But then it basically, and here are the basic building blocks that I just want to show you again, because I will touch upon them before. So you have your input, you have a convolution, right? Now this convolution here, typically what it's kind of like showing you the edges in this image. And you pass it through your nonlinearity. Always the nonlinearity is there so that you can make nonlinear relationships. Then what you do is something that is called pooling. And pooling can be, for example, you average you take every 4 pixels of your image, average them, and it becomes a single image. So you're basically, or you can pick the biggest, you take a bunch of images in your screen and you pick the strongest one. Some form of downsampling of your feature activation map. And then you have another convolution layer with the nonlinearity, and you do another pooling. So the idea is basically that you're trying to generalize, right? So if you're trying to recognize that a dog is a dog, it doesn't matter if the dog is looking at you like this, or if the dog is looking at you like this, or if the dog is looking at you from above. The idea is that what makes the dog a dog should be something that is not necessarily very detailed in space. So pooling is forcing the neural network to work with less information and trying to force a neural network to generalize. You're basically getting rid of information. You're telling the neural network, okay, fine, I gave you the input data and you did your first activations. Great. But I'm going to force you to make do with half that information. So you pick what you think is important because you're going to have to shed half of your input. And then you do it again and again and again. And you basically do this enough so that when you finally end up here, you have just a handful you have a very small image that you can feed through a fully connected neural network. So this is a fully connected. So you take the image here and you turn it into a vector, and then you do a fully connected thing, and you connect it to your output. So if you're doing regression of a single value, you at the end have a single neuron. If you're doing classification, you have a vector with each one of your classes, etc., etc. Now, traditionally, people used to do computer vision in kind of like, I think it's called the expert approach, which is where people will hard code what you think makes a dog a dog. Does it have 4 legs? Does it have, right? So we will kind of hard coding this kind of what us as humans think makes a different image a different thing. And here you have this, there is a very famous competition that still goes today, where you have in 2010, the great majority, all the people participating in this image classification contests were using the traditional computer vision algorithms. And you have percentages of success that go between 20% and 70%, right? They got better with time. But in 2012, you had the first application of convolutional neural networks to this problem. And it completely outperformed the traditional approach. It was so effective that the next year you only had 2 or 3 groups doing the traditional, and then since then your application is always neural network based. Because the cool thing is that now you don't need to hard code anything. The neural network is going to decide for itself what is the most important piece of information when it's doing those abstractions that I was showing you. So in our case, and this is one of the things that also goes when, as a researcher, this is where a lot of your energy goes into, is thinking about your information and what is the best way of feeding it into the algorithm that connects it the most effective way to your desired output. In our case, we had 2 paths of information that are parallel. So here you have the AIA image channels, our input, right? So what we did is we averaged all of them out, each one of them out, essentially getting something that looks like a total irradiance for a given channel, right? So you integrate them, each channel, 171, irradiance, something that looks like a total irradiance for the sun as a star in 171, in 304, in 1600, etc., etc. Now, presumably, you will think that the total solar irradiance in an AIA channel should be connected closely to the total solar irradiance in a wavelength that AIA doesn't see. And so what we said is we just did a linear model. It's just a linear combination of these inputs, and we connected them with different parts of the EVE spectrum. This already gave us some approximation to what the solar spectral irradiance is, right? For each channel, a linear input combination of the AI data. And so what we did is we work with the residual. Typically, these things work great when you use residuals. So you say the most naive and initial approach is to assume that just a linear combination of AI channels gives me irradiance in the EUV spectrum. And so what we did is we trained the AI images to try to predict what the correction to that linear combination of input channels is. And so with our application, the developed application of differential emission, measure inversion, and so on and so forth, we get something that looks like this. With our linear model plus the convolutional neural network, we get something like this, which is significantly better.
There's something I'm missing here. Are you telling the algorithm what wavelength band each AI channel corresponds to, or are you letting it try to figure that out for itself?
You let it figure it out. But what you do know is that this one is helium-2, this one is iron-15, this one. So the output is known, but the input, you just basically, I mean, in some sense, you're doing it.
It doesn't know what part of the E spectrum it's looking at.
No.
You're going to figure that out by looking at correlations.
Exactly, yeah. So the AI channels are not organized. Basically, what you make sure is that your input data and your output data always look the same, right? So where AI 171 is always placed in the same stack, but there is no information that we give to the neural network about exactly which wavelength it is, and in relationship with the other ones.
Except time. You say, at this time, here are the images, and here's the spectrum.
Yeah, so this is now casting, right? This is the same moment in time, but is EUV spectrum, EVE spectrum, and AI images.
The spectrum to train the model takes it from there.
Yes, exactly. And by the way, I didn't say this, but this is one of the things that you have to be extremely careful with is what you train and what data you use to train and what data do you use to assess efficacy, because it can be polluted. For example, if you think about the sun, and this is something that happened to me the first time that I tried this, is that the sun doesn't change so much over the course of a week. And so you can imagine that if you train with the first day of the week and test on the last day of the week, there is enough coherence informationally between the 2 days that the neural network starts cheating. And so you need to really, really, really work really hard to make sure that when the data that you use to test is in no way correlated or related to any of the images that you use to train. So we trained with 2011 and 14, and we tested on 2012 and 13. So that's why you see here 2012 and 2013.
Can you explain the residual again? I missed that. What is the residual?
So we're trying basically to predict nowcasts with the neural network, the residual of the most naive from the linear model, exactly. So the last thing is a little bit about this idea that the neural networks are not black boxes and can be mined for scientific insight. And so this is, I think, the first paper that was looking into detail at this, and I love just the name. GradCam, so all neural networks always have names, and they become famous and have, for example, we use an architecture called AlexNet. I don't know if you saw that in the image, but it was GradCam. Why did you say that? That's the title of the paper. And the idea is that why when I give this thing an image, why is it saying cat and dog or things like that? And now, there has been some work on this, but since most applications are practical, and this is actually just academic, I think there is a lot of things. I mean, basically, if we are going to use this for science, it's on us to come up with ways of using these networks for scientific insight. But basically, what you're looking at here is what is called a feature activation map, where you show an image, and it's trying to, you're looking at the part of the image that is most relevant to the neural network to make the decision that it made. And so in this case, you have for the cat, right? And in this case, you have for the dog. So you can see that in this particular application, it's looking at the entire body of the cat, whereas when it comes to the dog, it's just the face. And so these are kind of like things that are interesting when you're trying to understand what is the most important piece of information contained in your data that allows the neural network to make that connection that it made. So I'm going to show you like a first step that we did with this, which I think is very promising, but it's really like that, a first step. And it comes to this. Remember that I show you this informational path where you're doing the convolutional network downsampling, and so on, and then you have a fully connected network. But our data science mentor came with what I think was a super clever idea, is that at the end, my output is an array. This array is a single value of irradiance for helium-2, a single value of irradiance for iron-20, and so on and so forth, right? So he said, what happens if we get rid completely of this part? And we construct our convolutional neural network in a way that at the end, I have 14 images for my 14 channels. And the only step that I take between those 14 images and my 14 channels is integration. So just adding all the pixel up. So the interesting thing is that now, if you've built your neural network that way, you're forcing the neural network to come up at the end of all the process with an image that has the units of irradiance, the physical units of irradiance. And so here are those. So here at the top you have the AIA channels, pure, the AIA channels, 94, 131, 171, and so on and so forth. And here are the images that are quantifying irradiance for the different pure line channels that we were doing on the MEX spectrum. And the idea here is that maybe with a little bit more work, we could potentially use this to create spatially resolved if, right? If we how will the sun look like if we have a narrow band imager at each part of the EUV spectrum. And so here is, and you can see it's not perfect, but it's starting to look, it's doing the right things, right? Iron 20, which is mainly a flaring channel, is pretty dark, and the helium-10 with the 304, and so on and so forth. But this is where basically the neural networks can start informing and could potentially be used to get more. You can imagine that then you can use this to make temperature and density maps, right? With more channels than just the AI channels. So you have more information. You have better use of the information contained in the AI images.
Sorry, so the two bottom rows there were the calculations?
Yeah.
They're all Eve data.
Yeah, exactly. Just a single line in the Eve spectrum. Very narrow, extremely narrow band. So it's just the line. So what comes next? We are releasing the machine learning ready AI and HMI data that we used for all this from May 2010 to December 2017. So these are downscale and normalized, fixed for degradation, and making sure the sun is the same size in every image. Already as non-pi arrays, because almost all this is written for Python. For HMI and AI have the same angular resolution in the image, so they also can be collocated one on top of each other. We are going to plug the MEX-A emission line observational gap from 2014 onwards using this application. And we're going to working on producing a full EUV radiance spectrum. In this moment, we were only using 14 channels in the MEX-A. But the full MEX-A spectrum is 1,500 channels, which is challenging. I mean, we tried to do it, but it was very challenging to do. So we're basically solving this problem. We're looking into turning the nowcasting application into the forecasting of EUV radiance. And we're looking into the possibility of obtaining spatially resolved maps for the Eve channels. And so going back again to the message, measuring solar irradiance is important for us as a technological society. We lost our capability to measure part of the UV spectrum, but now, thanks to deep learning, we have recovered it back as long as we have AI. And neural networks are not black boxes and can be mined for scientific insight. And there is a lot of potential there, but has never been done because most of the people that are working with these techniques are non-scientists. And so if we want to gain scientific insight for these techniques, basically is on us. We have to come up with the ways. So there is stuff that can be done. And that's it. Thank you.
More questions in the back.
Yeah, for these multi-layer networks in a given application, how do you decide what the nonlinear functions are that will be used passing from one layer to the next? I mean, what informs that decision?
So there is a zoo of functions that you can use, but actually what people have discovered is that the actual form of your nonlinearity is not as important as the fact that your nonlinearity is there. And so that is something that is easy, is nice, because basically now, so you obtain similar performance whether you use certain nonlinear function of this other nonlinear function. And one thing that people have discovered is that the simplest nonlinearity that you can have is basically something that is a linear, a y equal x relationship in the positive and a 0 in the negative. Just that. That is enough for the neural network to capture. People were using sigmoids and the tangent and the arctangent, but actually the easier this function is, the simpler it is, the easier it is to derive, the faster the neural network trains. And so that's kind of like what is driving the choice of which nonlinearity to use. In this moment, the great majority of people use basically two lines with different slopes, one for the positives and one for the negatives that touch at 0. And that is enough for the neural network to capture. It's actually quite robust to the actual slope and to the actual. Now when it comes to the final neuron, actually people pick them according to the application. So when you have classification, so you say this is a dog, this is a cat, you want nonlinearities that are almost like a step function. So it just triggers a 1 or a 0. And so people use nonlinearities that are almost like a step function. It's just nothing and then something for the last layer. But if you're doing regression, then you basically keep just a strictly linear, things like that. So these are the things that basically what I want to say is that the bottom line is that the exact form of the nonlinearity is not that important as long as it is there. The simpler the nonlinearity, the faster you train. And then you may want to choose specifically the nonlinearity on your last layer, given your application.
Travis?
So your training set and your validation set are both sampling, sort of broadly speaking, near solar maximum, but the hole that you're trying to plug is closer to solar minimum. Are you having a problem?
That's why we, in the end, used in 2010 and 11 and 14, with the idea that at least for solar cycle 24, you're capturing solar variability. But that's something that we also put a lot of thought into.
Tom?
Yeah, the idea of filling in the entire 1,500 channels is interesting. I think that is a challenge, perhaps, for the computational method. But I think you need to talk to this guy here, Stan, about whether or not has any utility for the modeling. Because capturing those key lines, I mean, right now, most models key off of F10.7, for God's sake. So if you can capture those key lines accurately, that may be enough.
Yeah, we were thinking, for example, we could do the spectrum, integrated, do the integrated spectrum and the individual lines, absorption.
Keep in mind your ultimate application for EUV prediction and spectra. It's typically these atmospheric models.
Yeah.
Well, but he's after solar physics too.
Yeah, no, but I think you're totally right.
DEM and everything, right?
You can do, but I mean, there is a, yeah, you can deal with them separate. And I wanted to add something also to what you said. One thing that you can imagine is, I mean, one of the questions that you can ask yourself is whether irradiance is a global. It's if you have an image of the sun, do you have kernels of irradiance that you add over? Basic structures that you add over? And so solar cycle variability could be that you have more of these kernels versus these kernels. I'm thinking active regions, for example. So it is possible then that if you train only on a given year, you may have seen enough of those basic conceptual kernels of irradiance. We tried training only on 2011 and testing on the rest. And it works actually quite well too. But the solar physicists, we were like, no, but the cycle, there's maybe something in the cycle, so let's use this and this, and that's kind of what we sell.
You were referring to in your lecture that the human brain works similarly. How do people know that?
I think this just by doing experiments on perception, showing at people. So I'm not an expert on this, but I did take a class on human perception, how the visual cortex works. Yeah. And for example, the idea that we are optimized to detect edges, for example. And so, for example, and how we are basically assembling. I have to actually, I don't know the answer to this question.
And red too, right? We're optimized to detect red.
To see red, the color red, yeah.
Not everybody.
No, but I think, yeah, so edges, so our eyes are moving so that we find edges, and that's what we use to take something that looks, something that is, I don't know what the resolution of our eyes are, let's say 4K by 4K, right? If you convert that into a map of edges, then the amount of information that you're handling is much less. And so I think that the two basic operations that our eyes do are edges, and also there is something about we blur. I don't know how people measure this, but I remember seeing this in that class. We take our image and we blur it, and we also take the image and we make edges. And with both of those, then we start combining to produce a conceptual map of what we're seeing.
Is that how we tell the difference between the Chihuahua and the
Well, I mean, you can see why it's so hard. I mean, it's hard when you see them. They look so much like both.
I thought it was a muffin, not a cookie.
It's a muffin, yeah, it's a muffin. But, so this is,
Well, especially dogs that are optimized for their culinary aspect.
no, but it is fascinating because there is this exercise that people did. There is something in the neural networks that maximizes an output that doesn't necessarily look like the output itself. So the quintessential dog for a neural network doesn't necessarily look like a dog. Some people did this very interesting experiment where they train a neural network to do image classification. And among the classes were turtles and rifles. And so then they started this game where they 3D printed a rifle, but they started tweaking the rifle in a way that the neural network was saying that is such a turtle for sure. But to us, it looks like a rifle. I show it to you, and it looks like a rifle. And that basically means there is something in the textures that the neural network is paying attention to. Another very interesting experiment was you can see different. Among all these layers, you can basically see what a specific layer is reacting to. There are ways of doing that. And someone was looking at face recognition, and they found that there was, so they will have a camera, and a person will come into the image, and different parts of the image will light up for different features. And there was one where the person will come here, and it was just two bright patches on the chest. And so people said, oh, that's because it's looking at chests or something like that. But then it turns out that if the person will do this, then that neuron will deactivate. And so what the neural network was reacting to was these wrinkles. So they probably didn't show the neural network naked people. Every time, all the samples of faces were people that were clothed. And when you have clothes, almost every time you have wrinkles here and near your shoulders. And so the neural network thought that that was a very important piece of information for making image recognition. And so it's interesting. It's all these things, I think, I feel that's where we can try to gain insight. It's out of all this input, what is the most important thing for you? And then we can make sense of it and say, oh, okay, then maybe these are the quantities that are relevant, or these are the structures that are relevant for this phenomenon, things like that.
Yeah, these pictures were probably just all taken with cell phone cameras. Okay, let's have a last couple of questions. Stan, sure.
Well, I think your point about networks and humans is just that you can fool the neural networks and fool the humans. It doesn't prove they're the same thing, but you can still fool them.
No, but then I also think that's why having the neural network with the human is the powerful thing.
Yeah.
Right? The educated researcher.
Getting back to the science for a minute, I mean, I think that in response to the question, like, what's the most important thing for center, the EUV, you could only have one thing. That thing would be the helium-2 304 that's in that facility. Because, well, it's a great proxy, because well, there's almost half the energy right there.
Right.
So it's a great proxy for itself, and it happens to correlate pretty well with a whole bunch of other stuff. So if you had that, and you had that pinned down, you have an excellent thing. So you can distill this kind of information down. It's not pretty simple.
Yeah. Well, we have. I show you helium too.
Or you can integrate it with bands or whatever. But then the other thing I'd just like to say is that I actually thought you were going to talk about a different gap, which is the spectral gap between approximately 1 and approximately 6 nanometers, which is only characterized, but there's a variety of information. There's images of lines of bands that are related features in that regime. There are snapshots from, say, rockets, parts of that spectrum, and there are, and of course, there's measurements from GOES XRS, Yoga, there's tons of information out there. And there's long-term, fairly stable broadband measurements of what the integral of that band might be. We still don't know quite what the spectrum is in there. Without knowing the spectrum, we don't know how to distribute that anymore. And so it strikes me that maybe that problem could also be a target for this type of approach.
We will need to talk, because you need to always have the truth. With this particular technique, there are other machine learning techniques that are trying to puzzle a puzzle out of overlapping different pieces of information.
There's a couple of snapshots, right? There's a couple of, quote, true snapshots. And you need 10,000.
Yeah. No, I mean, there are things that can be done, but it is possible. I mean, we will need to talk and see what the data space is. Yeah.
But you're familiar with a lot of them, sure.
Yeah.
Okay, I'm going to close the discussion here. Andres is not going anywhere. He's around in Boulder, and he's usually here, typically on Fridays around donut time. All right, so let's thank Andres again.